Okay, hello all. Today we'll be looking at the next topic, that is Fibonacci heaps. So we have already seen binary min heaps or max heaps, and usually we took the example of min heaps, and we saw that most of the operations are good except for merging of two binary heaps. And then we moved on to the next topic, that was binomial heaps, which is also an efficient way so that you can merge heaps in effective way. Okay, so these are the variations of heap that help you in merging of two different heaps. One was binomial heap that we looked in the previous class, and this one is binomial. Now the next one is Fibonacci heaps. And Fibonacci heaps is an amortized data structure where you can see that some of the operations have the least cost at the expense of, you can say, some operations that are heavily complex. So this is a comparison chart of binary heap, binomial heap, as well as Fibonacci heap, and the amortized cost complexities are displayed here. So you can see making a heap is basically O of 1 or theta of 1 for most of the cases, whereas insertion takes log n, and it also takes log n in binomial as well as in binary. But in Fibonacci, the amortized complexity is O of 1. Finding the minimum is O of 1 in a binary heap, but in a binomial it is log n, and Fibonacci it's very less, that is amortized complexity is only O of 1. Extracting the minimum takes log n in all the three cases, whereas a union or merging is O of n, that is the highest complexity in binary heap, because that is worst case complexity. It's not possible usually. So that is why we went for different data structures like binomial and Fibonacci. And you can see in binomial, it takes O of log n, but whereas in Fibonacci, it takes only O of 1. So you can see extract min is only one, which basically takes more time, or the complexity is more when compared to the other operations in the Fibonacci heap. Then union, just now I said, then decrease key and delete. Decrease key also takes O of log n in both the cases of binary and binomial, whereas it is very less in amortized cost is very less in Fibonacci heap. Delete takes O of log n in all the three cases. You can see delete in Fibonacci heap makes use of extract min also. So that is why the complexity is almost the same. So basically what we do here is we do not, that is a Fibonacci heap will have a specific arrangement of how the tree should be arranged, how many number of children should be there as a balance factor, right? But when it comes to all the operations in a Fibonacci heap, we do not rearrange the tree unnecessarily. We leave the tree as it is. But when a case of decrease key or extract min comes in, we usually perform the combination or the union operations are basic. We call it as consolidation. The consolidation operation takes place only in the extract min. That is why it is more complex than the other algorithms. So you can see some of them are given less cost, whereas the others are given more cost at the expense of that cost. Now we'll see what is a Fibonacci heap. It's a collection of min heap ordered trees where each tree is rooted but unordered. That means there is no ordering between the child nodes like in an ordered binary tree. You can arrange it in any particular manner. Now, what are the things or the elements or attributes of a node you can say is, say, for example, if you have node X, then it will have a parent pointer that is denoted by P of X. So you can see a node X will have a parent pointer P of X and a child pointer child of X, which points to arbitrary child of X. Now, usually all of these children of any particular node, they're linked together by a circular doubly linked list. See this, a circular doubly linked list. So you can have every node Y will have a pointer like left of Y and right of Y to keep track of its children. It's not like the left child, right sibling. We learned that mechanism in the previous lecture in binomial heap representation. Here you have internally, it will be represented by a circular doubly linked list. I'll show you an example of how it looks like. See this. Even though this is the basic idea of how a tree looks like in a Fibonacci heap, you can see here that when you implement it internally, this is how it is going to look. You can see every child, say you take any child here, 18, it is linked together with the other its of its siblings by using a left pointer as well as a right pointer. That is why it is a doubly linked list. And also you can see the last node is linked together to the first node and the first node is linked together to the last node. That is why it is circular also. So you can see internally it is a circular doubly linked list representation where all of them keep track of each other. Okay, so this way, if it's a single node child, this is how it will be represented, and this way, and so on. See, so this way, and the same happens for the root list also. All of you know that we have a top level layer like this, which is known as a root list. So basically, what is a Fibonacci heap? Fibonacci heap is basically a number of Fibonacci trees. You can see a number of trees are there, which keeps track of some property. That is why it's known as Fibonacci. And this Fibonacci, and among that, you'll have one node that is the most minimum because it is a min heap. Okay, so you have a number of Fibonacci trees of different degrees or same degrees or whatever it is. Usually, finally, when you rearrange the tree, just like in a binomial heap, you should have different degrees. It should not be the same. But this is an intermediate stage. That is why you can see some of the nodes have same degrees. See? And one of them will be marked as min of h. Why? Because that is the most minimum um, among all the root nodes. So the root list also is joined together by a doubly linked list, and that is circular also. So you can see here, each node will have a parent pointer, it will have a child pointer, and the children will be linked to each other using a pointer named as left and right. So basically, X will store the node that is at the start of the uh, list. So any of the one of them will be just like I said in the left child, right sibling. It will keep track of any one of the child, and each of the children will keep track of its siblings. Okay. So that is what is written here. X basically stores a pointer to the start in this list of its children, and the children will keep track of its sibling using the left and right pointers. Now the roots are also connected with the circular doubly linked list, again with its left and right pointers, that is there. Then the Fibonacci heap is defined by a pointer min of h, which points to the root of the tree containing the minimum element. That is what I said before. You have a set of trees which all contain its own parent or root child. And among that, the most minimum one, which should be the root of the entire heap, should be tracked by the pointer named as min of h, where h represents the heap tree. Now you'll have something known as a variable known as n. What is n of h? It is for keeping track of how many elements or nodes are there in the heap. The total number of nodes in the heap are kept track of n of h. So whenever you add or delete a node, every time you have to increment the value of n of h or decrement the value of n of h depending on adding or deleting. So that is one thing. So this is a basic look of how a Fibonacci heap looks. Now, every node X also has few additional variables or elements that is known as degree of X. What is degree of X? Degree of X stores the number of children of X. The number of children of X. That we already know. Any node, that many number of children, how many number of children it keeps track of, that is stored as a count in this degree of X. Now, mark of X. This is a very important concept because it's only pertaining with Fibonacci heaps. So in order to understand this, we need to move to the algorithm, but I'll just tell you what it basically means. Indicates whether X has lost a child since the last time X was made the child of another node. So you can see here, even in this tree, can you notice that some of the nodes, most of the nodes are in colored using gray color, but some of the nodes are marked in a special color, say black. Maybe other textbooks, they'll simply put a marking, say a variable here, say M, something like that to indicate it is marked. Or either when you're doing it in your exams, you can just shade it or you can somehow denote that this is a mark. So what is meant by a mark node? Mark node is basically when you are using the operation decrease key. Okay, suppose that due to some reason you want to delete this node from this tree. Okay, you're deleting this node or extracting it from the tree. So whenever a parent loses a child, you denote it as a mark node. Whenever a parent loses one of the child, it may have number of children of which it loses one of the child, maybe due to some operation like decrease key. And what you do, whenever one of the children is being lost, you just denote it as marked. to show that it just recently lost a child. Okay. Now, suppose that one more option, suppose this one has one more child and it is still unmarked, or it was unmarked, or if it was unmarked, sorry, it will not be unmarked. When you lose this child, you naturally mark it as marked, or you shade it as black. And once this is gone, suppose that this 38 had one more child and it is in a marked state. And it is and due to some reason, you have to remove this child also. So what is the meaning of mark is that when it lost its first child or one of the child, and you marked it as black and you did not cut it from the tree, you did not cut it from its parent node. It is still in this position with its respect to its parent. Okay. അപ്പോൾ ഒരു ചൈൽഡ് ലൂസ് ചെയ്തപ്പം മാർക്ക് ചെയ്ത് വെച്ചു. രണ്ടാമത്തെ ചൈൽഡ് ലൂസ് ചെയ്യുമ്പോഴത്തേക്ക് now we cannot make this, or we cannot keep this node over here. We'll have to cut it from its parent. Okay. So it is an indication whether the black color shading or the mark node indicates that it recently had lost its child, and still it was kept with its parent. That is, you did not remove it from the tree. You kept it as it is. 38, even though it was marked, it was in this position from that time being. But later on, when it has to lose one more child, that is this one, you will have to remove it from the tree. You cannot keep that because the tree is already unbalanced. You're giving it a chance to stay like that for some time. Okay. And if it has to root one more child, then that node cannot stay there. Then you have to remove it entirely from that position and make it to another level. Or you have to remove it and bring it, we usually bring it to the root level. Bring it to the root level so that you can merge it together. So you're giving a chance, or you can say you're giving a chance for it to stay there, even though it lost one of its child. And by informing others, by shading it as black. Okay, so that is a basic idea of that. So basically, what is a mark node? It's a node becomes marked when it loses one child due to some operation, but it is not yet cut from its parent. What is a parent of 38? It was 3. It is not cut from its parent. Now, once a mark node loses another child, suppose that it had to lose one more child when it was already marked, then it is cut from its parent. So this is the basic idea behind mark nodes. So we denote the mark nodes by color black and the unmarked by color gray. In this particular PPT, I've used that. In different maybe scenarios, you may find different other color combinations. So the newly created node, usually when you add a new node to the list, it is always what? It is always in gray color. That is unmarked situation. Because the first time a node comes to a tree, it is always unmarked. Then you can say a mark. Now, how do you remove this mark? That is also you have to know. Once a mark node, it will become unmarked whenever it is made the child of another node. So whenever you remove it from, it's a 38 was already marked. Now you're going to remove it from here and you're going to bring it to the root list. You have to unmark it and then bring it here. Okay, and then when you combine these two together, maybe these are of the same degree. So when you're going to combine it with 7 or something, then also it has to be unmarked. So we'll come to those scenarios when you learn the algorithm. Okay. Now, in order to learn this entire thing, we need to know what is the amortized analysis of each operation. So the amortized analysis basically uses the third method that we learned, that is not the accounting method, but the potential method. So the potential method was a change in the state between two different scenarios. So if you have a current state and you add some or you delete some or you perform some operation, and in what is the change in potential energy in the next state. So let us see. You can see it is denoted by phi of h. What is phi of h? Phi of h is basically the sum of two different things. One of them is, you can see here, it is the T of h. What is T of h? T of h is basically the number of trees in the Fibonacci heap. Say, for example, how many trees are there in this Fibonacci heap? You can see there is 1, 2, 3, 4, 5. 5 trees are there. So the count of the number of trees in a Fibonacci. Now, what is M of h? M of h is the number of mark nodes in h. So the number of trees in the Fibonacci heap accounts to the state of the tree, because you keep on adding new, you keep on deleting some. The number of trees are what matters, right? It causes a great change in the look and feel of the tree. So you can say that that is one of the factors that contributes to the potential function. Another factor that contributes is the number of mark nodes. So the number of mark nodes that you have here, because as the number of mark nodes keeps on losing its child, you have to rearrange the tree every time. Suppose 26 already lost a child in the previous state. Now it is going to lose 35 again. Then you have to remove this from here and bring it to the root level of the tree. That is what we're going to do. So you can see the number of trees in the Fibonacci heap will also increase. So that is a change in the potential energy. Got it? So whenever you're trying to remove a mark node from its original position and bring it to some other thing, it is also increasing the size of the trees, number of trees. So that is why it is 2 times mh. Why it is 2 times is because if you know, if when you come to the algorithm, you'll understand that when suppose that I'll just simply say what it means. Suppose that 35 is lost for 20. 26 is already a mark node and 35 is removed currently. Now, when 35 is removed, you have to cut it from its parent. So that takes a unit cost. Okay, 1 unit of cost for cutting it from its parent. That is removing it because 26 is marked. Why? Because it already lost a child before. Now you're again removing 35. So this has to be removed from this particular position because it cannot stay in that position. It keeps on losing its children, then it will be unbalanced tree. So you remove this from here, that takes 1 unit of cost. Then you have to unmark it and bring it over here in this level. So you bring it over here. That takes 1 more unit of cost. So you have 2 units of cost whenever a mark node has to be rearranged. Okay. So what happens here is you take this and you apply 2 units of cost to it for the operations that have to be done when you remove a mark node from its original position. So that entire thing is basically the number of the, now this will also increase when you bring the mark node to the level of the root list. So അവിടെ നമ്മൾ treesന്റെ എണ്ണം കൂടിക്കൊണ്ടിരിക്കും mark node position മാറുമ്പോൾ tree number of trees also will increase. So you can see these two things are what contributes to the potential function of a particular scenario. Now, it's also mentioned that D of n is basically a degree of any node. The upper bound on the max degree of any node in an n node Fibonacci heap. You have maximum n nodes in a Fibonacci heap. It is always log of n. Okay, LG, log to the base 2 of n. So you can say the upper bound of the max degree will not go beyond log of n. That also we have to keep track of. Now, what are the different operations to be done? Create an empty Fibonacci heap, insert a new element. You can merge two Fibonacci heaps, extract the minimum element from the Fibonacci, decrease the value that we saw in the previous, like we saw in binomial, then delete an element. So we'll see what are the algorithms pertaining to this. So first one is creating a Fibonacci heap. Let's make fib heap is maybe the name of the algorithm. So this actually what it does, it just creates an empty Fibonacci heap and label it by say H. Okay. Now in order to do that, we have to create an objective. So we need to know what is the minimum of H and we need to know what is the number, because this keeps track of the entire tree, not of the entire heap, not just a particular tree. So for a Fibonacci heap, the global variables that pertains to the heap are basically min of H and n of H. What is min of H? It keeps track of the most minimum element among all the trees. The root node, which one is the minimum? Initially, because it is empty tree, we label it as nil. Now, what is n of H? The number of nodes inside the heap. Is there any tree inside the heap when it is empty? No. So n of H is also 0. So what is the potential energy? Is there any change in state? No. So because there is no change in state, the change in potential energy is 0. Basically, you know that the amortized cost is nothing but the actual cost plus the change in the potential energy. Now, what is the change in potential energy? It is 0. So when you have a constant value, say cost C, you always denote it by a constant time is always denoted by O of 1. So amortized cost is equal to the actual cost, that is nothing but O of 1. Okay. Now inserting a new element. So suppose that this is our existing tree. Okay. Now I'm asking you to add a new element. Now, usually when we add a new element, we add it to the left of min of H. You know that every root node will have a pointer left and right. Every node will have a left and right pointer. So towards wherever is a min of n, towards the left or right of it, we add the, depends from book to book, but in this textbook, they usually add it to the left of min of. So immediately to the left of the minimum element, we add it. Now, when we add it to the left, in order not, because if we add it somewhere else, we'll have to again search the entire tree to see which one is the most minimum or next, something like that. So immediately to the left of min of h, we update it. Okay, so you're going to add it where? You're going to add it here. So what is a new element? We're going to insert 21. Make a heap out of 21. X is the element. X is the element. We create a new heap, say h dash, and we are going to add it to this. Okay. So just insert the element in this. That's as simple as it. So what you have to do is just add 21 over here. Now, just find out immediately added element is x, right? And the previous minimum element is the value min of h. So take the min of h value and compare it with the element that we recently added and find out the minimum among these two. If suppose that the value here was 1, then naturally min of h has to be shifted to this particular tree, right? But currently it is 21, it is greater than 3, so there's no need to transfer min of h. Okay, now you can see there are so many nodes with a single degree, the 0 degree. Okay, there's a node with 1 degree, there's a node with 2 degree, there's a node with 3 degree. These are different, but these are the same. Usually, if it was in a binomial heap, we would have combined it. We would not have the stage, but here we do not combine the items in the root list. We leave it as it is. That is why now the tree will become unbalanced, even though it is unbalanced. At some particular stage, we have to rebalance all of them. So the cleanup is basically done only during the extract min operation. That is why, if you remember, extract min takes O of log n. So if k nodes are inserted into the tree, h into the heap h, it becomes basically a linked list with k single nodes. So whenever you're inserting a node, you just keep on adding it like this. If there are k nodes inserted, you'll have a linked list which will have how many nodes? K nodes and so on. So this way, you just simply add the elements. Now, this is the algorithm for that. The things that you see here in the beginning are simply initialization procedure. The question is to create a new node X and just add it to the heap. So what is the first step we are doing is what is the initialize X? Degree of X is 0, parent of X is nil, child of X is nil, left of X is X itself, right of X is X itself, and the mark of X. Mark is whether it has been a marked node. Initially, when a new node comes into the tree, it is always unmarked. So mark of X is true when it is marked. So here mark of X is false. Why? Because it is a new node. Now concatenate the root list containing X with the root list H. Okay, you bring X into the root list and you bring it together. Concatenate means you add the pointers, the doubly linked list pointers here and there, make it circular, etc. It is circular already. You can see in step number 4 and 5, the node X that you created, it is circular to itself. Okay, that is it. Now, when you add it to the root list, you have to mark the pointers left and right like this. So you have to add the left and right pointers. Okay, now you can see min of h is nil or the key is less than key of min of h. Suppose the value that you recently inserted, we inserted 21. What was the earlier value? It was 3. Now, by any case, if the tree was empty and you are inserting the first node in the tree, okay. So when min of h is nil means what? You do not have an existing tree. It was initially null. Okay. In that case, or the existing element or the existing min tree has a greater value than the newly inserted value. If those case comes, then you assign the new node as min of h. അതായത് ഇവിടെ നമുക്ക് 1 ആയിരുന്നു എന്നിട്ട് 3 ആയിരുന്നു പഴയ വാല്യൂ എങ്കിൽ ഇനി പുതിയ മിൻ എന്ന് പറയുന്നത് 1 ആവും. 3 എം ടി ആയിരുന്നെങ്കിലോ പുതിയ മിൻ എന്ന് പറയുന്നത് തന്നെ 1 ആവും. അല്ലെ 3 എം ടി ആണ് വേറെ മിൻ വാല്യൂസ് ഇല്ല 21 ആണ് നിങ്ങൾ ഇൻസേർട്ട് ചെയ്യുന്ന ഫസ്റ്റ് വാല്യൂ എങ്കിൽ പുതിയ മിൻ ഓഫ് എച്ച് എന്ന് പറയുന്നത് 21 ആയിരിക്കും and so on. So that is one case. You have to, special case you have to check step number 8 and 9. So you initialize. So what is the step number 1 to 6? Initialize everything, bring it to the root node. When you bring it to the root node, also check whether it is an empty tree or the newer value is lesser than the existing min, then reassign the min pointer. And the last step is a common step. Sorry. And the last step is a common step. What is this? N of h is incremented by 1. I already told you what is n of h. N of h is the number of nodes in the entire tree. Currently, there are say 10 nodes. Now, when you add one more additional node, it has to be incremented by 1. So this is the basic idea of inserting. Now, what is the amortized cost of insert? You know that the actual cost is just O of 1. Actual cost C will be O of 1. the change in potential is also +1. So when you insert one new tree and it does not have any mark node, basically the amortized costs also become O of 1. So we'll see how this is done. So suppose that H is the input Fibonacci heap. Okay. And after you insert this, so initially you had a tree like this. Okay. You had a tree like this. And after you insert a new node into this tree, the tree will become something else. So this is known as H and this is known as H dash. So what is the change in potential energy from H to H dash? That is what we're trying to find out. Suppose that the actual cost of the operation is O of 1, that we already know. Actual cost of operation, because we just have to create a node and insert it. There is actually no cost involved, it's just a constant cost, that is O of 1. So we can say that for the new tree, what are the number of trees inside the heap? It is incremented by 1. The previous stage you had T of H. In the old tree, you had T of H nodes and you had marked nodes M of H. When one more node is added to this old tree, what is the change in number of trees? It will be incremented by 1, right? So the old tree number of trees plus 1 for the new node that is inserted. Then you have M of H dash. Is there any change in the number of marked nodes? No, it is the same as the old heap itself. When I say tree and heap interchangeably, please don't be mistaken. I'm basically talking of heap itself. Okay. So in the new heap, it is nothing but the number of trees in the whole heap plus 1. And the number of mark nodes in the new heap is same as the number of mark nodes in the old heap. There is no change. Now, what is the change in potential energy? We know it is, we have to subtract. This is the previous state and this is the current state. So the change in potential energy is current state minus previous state. So what we do is the potential energy of the current state minus the potential energy of the previous state. We just have to subtract these two. So just add the values here. You'll get T of H. You know that phi of H dash is T of H dash plus 2 times M of H dash minus T of H plus 2M H. Now, what is the change in this? So substitute the values here. For T of H, we can write T of H plus 1. So what happens is it becomes T of H plus 1, the whole, plus 2 times M of H dash is nothing but it is M of H itself. So 2 times M of H minus this part. Okay, that is nothing but T of H minus 2mH. Now you can see T of H and T of H cancels out, 2mH and 2mH cancels out. Now what is left behind is simply a 1. So you can say the amortized cost C cap is given by the actual cost plus change in potential energy. What is the actual cost? We know it is already O of 1 and we're just simply adding a 1 to that. So a constant added to a constant is nothing but O of 1 itself. You don't have to actually measure whether it is 2 times, 3 times or something. It is basically a constant itself. So amortized cost of insert is, what do you say? O of 1. Okay. Now next is finding the minimum node. Finding the minimum node. The minimum node of a Fibonacci heap H is given by the pointer min H. So we can just actually go and find it very easily. Just have to look at the pointer min of H and we can in actual time O of 1, we can just simply find it. So because the potential of H does not change, amortized cost of this operation is equal to the actual cost. So you can say the amortized cost is equal to the actual cost itself, and there is no change in potential because we're not changing anything, right? We're just going to a particular location and finding it. So this one is actually nothing but you can say it's just a 0. So you can say it is C itself, that is nothing but O of 1. Okay. Now, how do you, there's nothing to describe as algorithm here because you just have to go, you're just looking or peeking at a particular point, that's all. Now, next algorithm is merging of two heaps, or that is union or joining or whatever. So suppose that you're given two heaps, say H1 and H2, and you know that they have different root lists. This is one root list in H1, this is another root list. So when you're trying to, you have 3 trees here and 3 of them here also. And we're trying to merge them together so that in total they'll become a 6 tree heap. Okay. So you know that the root list are circular, doubly linked list, so they can be easily concatenated. You just have to add a pointer here, here. Then you have to add a pointer from 23 to 21 and 21 to 23. That's all. There's nothing much to do. Okay. That is why merging is easy. It is not similar to the merging of a binomial heap. Why? Because in that merging, we had to combine the nodes that had the same degree. But here we are not doing that. Okay. Now, when you combine all of them together, what has to change? Another factor that has to change. So you're combining this together. You have two different min of fetch, but that is not possible once it is combined. What you have to do? You have to search and find which is the most minimum. You know that this was the most minimum in the first tree, and you know that this is the most minimum in the second tree. So you just have to compare these two min of fetch and see which one is the minimum among these two. Okay. So just compare and see which is minimum. So just write min of. Find the min, this mathematical operation that is min. Min of h1 and min of h2 are the two pointers. So the values are 17 and 3. Find the minimum among these two, that is 3. So the new min of h, now the new tree is called as h instead of h1 and h2. And we can see that it is combined like this. And like I said before, the way they have combined is a bit different. They have connected 7 to 23 and they've arranged it in a different way. So I think that doesn't matter much, but this is how they've arranged the tree in a different matter, not like I showed, like combining these two and then combining these two. They have arranged it in a different way. So in some order, they have arranged it. You can just look into in detail yourself. Okay. Now this is how they have performed the union. First step is create an empty heap H. Okay. And the first tree is H1 and the second tree is H2. Just assign min of H of the new empty heap as like this. First add the first tree. Okay. Then you concatenate the root list of H2 with this. So initially you have H1, which you merge into H. And then so now H1 is copied onto H. Okay. Now you bring in H2. And when you bring in H2, you see whether H1 was initially null or if there exists a minimum in H2 and the key of these two are compared, by any chance you get a newer minimum, as reassign the newer one as the new minimum, whichever it is. So if the initial tree was nil, then there's nothing else to do. The second tree, because if this was null or nil and only this was a tree, then naturally this will be the minimum. But when there is an existing tree, you have to compare the roots of root means the minimum of both the trees and find out which is the most minimum. Otherwise, you already assigned H1 as a minimum. Okay. If you do not want that H2 does not have a greater element, then this step stays intact. There's no change here. But if H2 has a more minimum value than H1, then you reassign this. So these two are the if and else parts because initially we assigned it. Now, if you want to change it because this is minimum, okay, that is what we do here. Okay. Now, once you do for step 4 and 5 to find the next minimum, that is done. Either you get it in step 2 or you get it in step 5. Then we have to change the number of nodes. What is the number of nodes in the new tree? It's simply the number of nodes in the first tree plus the number of nodes in the second tree. N1, N of H1 plus N of H2 is N of H. Now, once this is done, you free the objects H1 and H2, that is the old trees. Just delete the pointers and all, and you return the. Now, in here, they haven't mentioned how they're concatenating it, but this is how they've done. Okay, just you assign the pointers. The detailed steps are not there. Just left and right and everything. In a simple language, they've written concatenate the root list with this. That's all. Okay. Now, this is the cost of concatenating. You can see the cost actually does not have any potential energy change. Why? Because the current state is this, which is a combination of H1 and H2 that we already know. And the previous state, we have to take the sum of potential energy of individual trees, individually heaps basically. Phi of H1 plus phi of H2 is the previous state. Sum of this has to be, you can say, subtracted from the current state. So that is nothing but canceling out, right? When it cancels out, you get a 0. So nothing, the cost is basically O of 1. Now extracting the minimum. Now this is one of the important algorithm because here you're going to get a change, right? Extracting the minimum is basically, we found out how to find the minimum. That was just going and finding out min of h, the value or the key value under min of h. It takes O of 1. No cost is involved. But when it comes to extracting, you're deleting something from the tree. So when you perform an extraction of min of h, you can see here min of h here is the most minimum element, that is 3. When you're going to delete this node, you can see that These are the subtrees of this, or the children of this particular tree, fib tree. Now, this cannot stay in a level below once this is deleted. So you have to bring it up to the root level. So that involves some process. So we'll see what is done here. Now, when 3 is deleted, there's a subtree at 18, 52, and 41. Okay, we bring it up to the root level. So 18 mark 3, 52 mark 3, and 41 mark 3, all of them are brought up to the root levels. That is step number 1. Now, step number 2. Remember, step number 1 is deleting the min node and bringing all the children to the root level. That involves a cost. Okay. Now, next is consolidating so that no two roots have the same degree. The next thing is you have to, this is just like union, what we did in a binomial tree or a binomial heap. But this is known as algorithm consolidate. Consolidating means combining the trees that have same degrees. So the root nodes which have the same degree, we have to so you traverse the route from min towards right. Okay, wherever is the min, you traverse the tree. And if you find any of the two roots with the same degree, and the key of one of them is lesser than because it's a min tree. I'll show you an example simply. Suppose that you found these two are same. Which one will you make the root node, 23 or 17? Naturally 17. Why? Because this is a min heap, right? So when it is a min heap, 17 has to be kept in the root list and 23 has to be brought to the left of it. That is, once you remove this, you bring this here and bring here and link it here. Okay, that we already learned binomial link algorithm in the previous. So similarly here also we have a fib link. So we have to find out whether x is lesser or y is lesser. Whichever is lesser, the lesser one has to be made the parent node and the other one has to be made its child. So that step is what is written here. Okay, all these things. So you just bring traverse, find out the same degree, find out which one is lesser. If x is lesser than y, then x has to be made the y has to be made the child of x. So if x is lesser, then make y as the child. If y is lesser, make y as the root and x as the child, whichever be the case. Now, once you do this, when you, this was initially the degree of this was 0 and the degree of this node was also 0. Once you remove it and bring it here, now what is the degree of this node? It becomes a one child node, right? So the degree has to be incremented. That is what is done here, increment the degree. Unmark y if marked. Suppose that you're removing it from here and you're bringing it here. Suppose it was a marked node, then you have to unmark it. Okay, that is also one of the steps. Now, in order to do this process efficiently, what we do here is we create an array known as A. Okay. And what is the size of A is basically the number of degrees that are available. So whatever is the maximum degree of a node from 0 till the maximum degree of you have a number of trees of different degrees, whichever is the maximum degree that it can accommodate, that is the size of the array A. Okay. And at any time, you can say, if you take any particular position K, that means this K is basically the degree of that particular node Y. Okay. So degree will be the connected to the tree that has the same degree. So I'll show you an example, you'll understand more. So in step 2, once again, what are we trying to do? No two roots should have the same degree. That is, this tree should be changed in such a way that once these two are combined, they become a degree 1 tree. That is same as this one and same as this one. So you have to combine again and again till all the degrees are different. Now, once you do all that, the last step is update the min of h. Okay. So this is the array A that I was talking about. You can see what is the maximum degree that it can go up to is maybe say 3 or 4, nothing more than that. So we should know what is the maximum degree it can occur. So you have an array A which has size of 4, indicates degree 0, degree 1, degree 2, and degree 3. That is the maximum it is allowed. So all these degrees are marked and we create a pointers to this. So how do we start this? You start from the min of h, that is the first node, marked it as current. Now find out what is the degree of this by looking at d of x. If this is a node x or d of current. Okay, d of current is nothing but 1. So you create a pointer that indicates this has a, it is already taken by 1, the degree 1 is already taken by this particular tree. Now move forward. The next step is current is moved forward to the next root list and see, find out the degree of this current node, and we found out that it is 2. So we mark it here. Okay. Now move forward. We found out the next node current is of degree 1. Sorry, degree 0. It has no children. So we mark it here. Okay. Now we again move forward, and when we try to map a degree to this, but we can see that only one time the pointer can be assigned. This is already taken. We have no option to assign this. So what is the meaning of that? That means you found another tree which has the same degree that is already there. Okay. So 23 had a degree 0. 17 also has a degree 0. That means they both have to be combined. Now, how do you combine this? You have to remove this from the root list. Why? Because this is x and this is y. X is lesser than y, so x has to be made the root node and 23 has to be made its child. So that is the next step. Now once you do this, next step is you try to map the degree. We're going to map the degree. What is the degree of this? It is 1. But can we assign it to 1? No, because 1 is already taken. Not possible. So what does that mean? You have a tree in the previous step where the same degrees exist. So again, combine it. Now, if this is x and this is y, which one is lesser? This is lesser, right? So that means to the left of 7, you have to delete this tree, means remove this from the root list. And to the left of 7, we need to bring 17 and 23. Got it? This is this way we arrange it. So when we arrange it, this is how it is going to look. So actually they extracted this and brought this here in the notation. That is one thing, because we are currently in a position pointed by the pointer current, right? So we brought that over here. Okay, so bring this one over here and we arrange it like this. Now, when doing this, every time we check for min of h, that is written in this algorithm. Every time we do this, we rearrange the pointer min of h. Where is it? Okay, update this one. Update min of h after every consolidation we have to do it. Okay, so now when you're doing this, you can see the previous min of h was 7 itself. So yeah, so we brought it here, and the same min of h is also updated here because we extracted from that position and brought it here. The only notation is different here. That's all. It's not on the left side, it's on the right. Okay, now next, can we arrange a pointer to this? What is the degree of this? 2. Is 2 free? No, 2 is not free. It's already there. That means we have to combine these two then. Okay. So combining these two, 7 is a minimum. So to the left of 7, bring 24. And the min of h is currently the same itself. There's nothing to change because 7 is the minimum. Now we keep on doing this for the next node that is acting as a current. Its degree is 1. 1 is free. So we can arrange 1 here. Then next one's degree is 0. 0 position in the array pointer is also free. So bring it here. Now next is 1 again. Now 1 is not possible, right? So we have to combine this 18 rooted tree and the 41 rooted tree. We merge it together. So we bring it here, 1839 and 41, 44. So this way we arrange it. So this is a basic idea. Now we move forward. The list is over or the tree is over. So we can stop. So this is how we combine by with the help of a array that maximum size goes up to the maximum degree it can accommodate. Now all roots are covered by the current pointer. So it is done. Now you find the minimum. This is what we are talking about. In the earlier case, we didn't have to change the min, but once the tree is over, you have to go because you merged two new trees together. We cannot know whether a new one has already come. So there's a possibility that a new min of h has come up. So you have to see whether the current existing root nodes, that is 7, 52, and 18, which one is the minimum, and reassign the min to that. So this is a basic algorithm for that. You can go through it. So it's very simple and it's given. So the first node is marked as Z, and if Z is not nil for every, because the question was to extract the min, right? For extracting the min, you're enabling it as Z. For every child of X, you add it to the root list. Okay, when you deleted 3, all the children nodes of this was brought to the root list, and we make the parent of that current every node as nil. Why? Because 18 the child was 3, 41 the child was 3. But once you delete it from the parent of all these 3 separate trees will become nil. Okay, then finally you remove Z, that is the minimum node, that is Z was 3, say for example, 3 if it was a node, and Z was a node that was acting as a minimum, and we are going to extract this from the root list and bringing all the children to the root list. Now, if you find that to the right of Z, you have Z itself. That means you can say it is basically the only child or something like that. Then you can say min of H will become nil. Why? Because 3 was the most minimum, and to the right of Z, there is no other thing. Z itself, you got it back. That means it's in a circular manner. If 3 is pointing to 3 itself means what? It's the only tree in the heap. If that is the case, then there is no more min, right? Because you deleted 3. 3 delete കഴിഞ്ഞാൽ പിന്നെ min of h മാറുമല്ലോ. You don't have min of h anymore. Now, anyone among these 3 has to become the new minimum node because 3 is already deleted. So that is a special case to check whether it was a one tree heap. Okay, there was the only tree in the heap was this rooted by the minima element. Otherwise, what you do is whichever is the right, which in the right of z, you find give any one of the node as min of h, and you perform a consolidation operation. And you all, and finally, when you come out of this, because you have deleted one node, you reduce the number of nodes in the heap. And finally, you return the node that has been deleted. So this is basically a for loop, which happens here. And then you delete the number of elements and reduce the number of elements and return. Now, what does consolidate do? This is the main function. Okay, what is consolidate? Consolidate is basically combining the nodes with same degree. So what does consolidate do is the main process. Extract min is basically rearranging and bringing it to the root level, reducing the number of nodes, etc. Consolidate is the main thing. So you can see here, I'll just go through each of the step. First thing is you can say, I'll give you a basic idea. You can see how in detail it works yourself. That is, you create an array. You create an array A, which has a degree varying from 0 to the maximum degree that is allowed. And initially all of them are nil. Okay. Now you have a for loop from here till line number 13. What does this for loop do? For every node W in the root list. What is every node W in the root list is what we are doing here. See, you have a current pointer and you move through every node in the root list like this, one after another. So that is the for loop that is given here. For every node W in the root list, you have to find another node that has the same degree and perform the combination. So for every node W, we initially mark it as X and we find the degree of X as D. So based on the degree of that node, we have to arrange it with the array, right? Suppose you have a 1 degree here, and then you have to go to the position 1 and arrange the pointer like this. So that is why we have to keep track of the node as X and another one degree as D. Now, while the degree of this is not nil, if it is not nil, it has already been taken by somebody, isn't it? Otherwise, we assign the degree like this. Okay, while it is not nil, that step is at line number 13. If it is not nil, that means somebody else is already there with the same degree. Then you find out that node, go to that particular pointer and find out that node and label it as Y. So our original tree, which you are currently tracking is X, and already there was another node with the same degree, then that is known as Y. So compare the key values of those, both of them. They haven't written the else part of this key value because they're exchanging X and Y. Suppose X is greater than Y, then you exchange the key values of X and Y. Why they're doing this is for linking it together. Suppose that you have two nodes of same degree, say 15 and 4. And you can say this is X and this is Y. Now what they're doing here is just exchange the root, the trees completely. So exchange X and Y means now this becomes X and this becomes Y. That's all. The label will exchange. What is the purpose of that? A binary else. You don't have to write else for that. Because of the exchange, what happens? X will always contain the lesser one. That is the basic idea. So what does fib heap link do? We have done the same thing in binomial heap. You just remove, suppose X is the smaller one and Y is the greater one. You remove Y from the root list and make Y as a child of X. That's all. And you also mark the node. If it is already marked, make it as unmarked. That's all. These are the steps we do in fib heap. So suppose X is greater than Y, you swap the labels of X and Y so that now X becomes small and Y is greater and you link it together like this. That is 4 in the left till 15 add. That's all. Suppose തിരിച്ചായിരുന്നെങ്കിലോ ഇത് already less ആയിരുന്നെങ്കിലോ, say like this. If this was y and this is x, and we are checking if x is greater than y. Is x greater than y? No. Then you directly skip this then part and come here. Come here and link it together. That's all. Bring it to the left of 4. If x was this one, exchange the labels and then combine it together and so on. Okay, I hope it is clear. Now, once you do all this, that degree will become nil, right? Because you earlier it was marked to a particular degree and you try to combine x and y together. Now it will be a new degree node. Now, what is that degree? It is given over here. So in order to that, suppose it was 0, x and y both were at 0 degree. Okay, both had 0 degree. Now, when you combine it together, the degree changes or increases by 1. That is what is written here. D is equal to D plus 1. The previous one, the pointer is made as nil because 0 initially had x. The A pointer, which at 0 was pointed to by x. You found another node that has the same degree. So you remove this link. That is what is known as A of D is equal to nil. Then you increase the degree of the newly created tree by 1 and reassign that node to. So now this is being, now instead of you remove this part and 0 is now pointed by the new tree, that is x. Got it? So that is what we do here. Now once you do all this, after for every node, for every current node, we keep on doing this. Okay, you complete all this and at the end, we reinitialize the min of that, min of what do you say, min pointer. And the next step is from line number 15 to 19. It basically rebuilds the root list from the existing non-nil elements of A of I. So basically, if you have A of I, any degree of, A of I represents each degree, right? 0, 2, 3, etc. Example. So if there is a non-nil element, that is, it is pointing to some tree, then you just rebuild the root list once again and find out which is the most minimum among all the new trees that has been created. So you just assign A of I to min of H. That's all. Whichever you compare all of them and see which one has the most minimum element. And that is what is done. And if min of H is nil or A of I is less than, key of A of I is less than key of A of min of H, then find out which is the most minimum and reassign min of H. That is all. So basically you can see there are three, I'll just delete. The summary is your first step is this one creates the array A of I with particular degree. And this step till this step is for finding out degrees of same degrees and combining it together. And the actual combination process is done here with the help of this linking. Okay. In this while loop. And after you've done all that, you need to reassign the root list completely and join all of them together and find the new min. And for that, you have for rebuilding the root list, you have this for loop where finally you find min of H as A of I, finding out the minimum element and reassigning min of H. Okay, so this is a basic idea of consolidate, and this is for linking together two nodes together. That is the minimum one is kept on the root and the left other one is kept on the as a left child. So that is a basic idea. Now, the complexity of this is actually a detailed step. So you can see the time taken for step 1 is basically O of D of N. O of D of N means the maximum degree. We are moving the array. If there are 0 to 3 elements, only 4 times we will be looking into the maximum. You can say the work involved is adding the in step 1 is basically if you delete a particular node, say I'll show you an example. Suppose 3 was deleted and it has 3 children. Okay, it had 3 children. So the cost involved here is just cutting out, extracting these and adding it to the root list. Okay, that is a step involved in actual cost involved in step 1. In step 2, when you are consolidating, you can see that basically the root list, what is the size of the root list is basically the degree of n. Degree of n is the children's degree. Suppose you had 3 as one of the node that is to be deleted, and it had 3 subtrees like this. The degree of this is d of n, right? D of n. Now, what are the number of trees in the Fibonacci heap is already given as T of H. What is T of H? The number of trees. How many trees were there? 1, 2, 3, 4 trees were basically there. Now you're going to delete extract. We're using extract mean one of the tree is going to be dissolved, right? And you're bringing the subtrees to the level above. So T of H minus 1 involves dissolving the minimum element and bringing these three, that is the degree of n, above. So you can see the size of the root list. So how many trees will be there now? We can see here 1, 2, 3, 4 was initially there. You deleted one of the tree, and because of that, three other new trees are going to come to the root list. So totally we have 1, 2, 3, 4, 5, 6 minus 1 that was already there. You can consider it as the same. So d of n plus d of h minus 1, that is basically the size just before step 2. Before consolidating, what was the scenario in the tree is all the existing trees plus the children that has been newly added, except for one that has been deleted. So that many number of trees will be there. So TH original roots before deletion, one deleted plus the number of children of the deleted one. Now, how many number of merges are possible? You can see every merge takes basically O of 1 time. So total, you can say the number of degree that has been brought together plus the total number of existing trees will be the time required for the consolidation. So actual cost, you can say it is around the time for step 1 is plus time for step 2. That is what we have to look at. So it is basically O of dn plus T of h. This minus 1 and all we can just ignore. That is a basic idea. Now, when you look at the potential energy, this is how it will come. We have to find the actual cost and the potential change also. So after you extract the minimum, once you have extracted the minimum, you can see that the potential energy is basically TH plus 2 mH we already know, where TH is nothing but it is dn plus 1. The degree of the nodes that came plus 1 and the existing mark nodes are also there. So the change in potential actual cost is given by this and the potential change is given by this. And once you subtract all of them, you'll get O of dn. O of dn, we already know that the maximum degree we told in the beginning can go up to log of n, only nothing more than that. So we arrange that the proof of this is actually omitted in the slide. So the D of n can maximum go up to O of log n. So the amortized cost is O of log n. So you can look into detail here. Then quickly we'll look at decrease key and delete also. Decrease key is one of the case where the mark node concepts come into effect. Okay. So what is meant by decrease key? We have an element x. We have to decrease it to some value, say k. Say, for example, you had an element 46 here. I'm asking you to reduce it and bring it to 45. Reduce it by 1. So when you reduce it by 1, it will become 45. Now, K0 is the min heap property is, suppose you decrease the value. Once you decrease the value, all of you know that heap has a property that its parent child, in a min heap, the parent should be lesser than its children, right? So min heap property, what happens here? It is not violated. Why it is not violated? Because earlier it was 46. This was a proper heap and it was 46. Is there any violation when it comes to 45? No. 24 is still lesser than 45. 45 is still lesser than 72. So there is no heap violation. So is there anything we have to do? No, we don't have to do anything. But this is the case where this was a subtree. Suppose I asked you to reduce something here. I asked you to reduce, say here, this one. I asked you to reduce 18 to 1. Okay, now when 18 is reduced to 1, is the min property change? No, because 1 is still less than 39, 1 is still less than 21, and these are lesser than its children, and so on. So the min heap property is satisfied. But there is another issue in the root list. When you bring a new lesser value, min of h has to be updated to the newer value, the lesser value, because 1 is lesser than 7, right? So min of h, we have to rearrange it. So that we can check whether the min heap the min pointer has to be changed if needed. In this example, it is not applicable because we changed something below the root list. Okay. Now case 2, the parent of x is unmarked. In this case, case 0 is what no heap property is violated. Now parent of x is unmarked. Suppose that you're decreasing the value of 45 to 15. Now what happened? Case 1 is that there is a heap property violation. Min heap has been violated. The min heap property is violated. In that case, 15 cannot stay here, right? Why? Because 24 is greater than 15. It is not a proper min heap. Now, what is the first step to do is you cut off the link between X and its parent and unmark X if it is marked. Got it? 24, look at the example. 24 marked ano? Allah, gray color, it is not marked. Now, what are we going to do? Because 15 cannot stay here, we are going to cut off the link between X and its parent of X. We are going to cut off the link. Okay. So cut off the link between X and X parent and unmark X if it is marked. X in എന്ത് ചെയ്യണം? Unmark ചെയ്യണം. X ഇപ്പൊ unmarked ആണോ? Yes, it is already unmarked because it was a normal node. It did not lose any child before. So, but suppose it was marked, suppose it was black in color, you have to unmark it also. That is what is done. Then next step is mark the parent. See, look at that. Because 24 just lost a child, you have to make sure that it is marked. 24 15 lose ചെയ്തപ്പം ഇനിയുള്ള children lose ആയാൽ നമ്മൾ ഇതിനെയും ഇവിടുന്ന് cut ചെയ്യണം. That is why we keep track of this mark node. So we just mark the parent. Now once this is done, we take this subtree and add it to the root node. So take 15 and 72 and bring it to this level, So that is what is done here, see. And 24 is kept as marked. So is this much okay? Understood? What we did? Decrease 45. This was 45 before. We decreased it to 15. It violated the heap property. So if this was already marked, you unmark it and cut it from here. And then you bring it to the root level. And if the parent was an unmarked one because it lost its child recently, you make it as black or marked. Okay, this is what we do. Now, suppose that the parent of X is marked. Now, suppose I'm asking you to decrease 35 to 5. Suppose this was a node 35 and we decreased it to 5. Now, cut off the link between X and its parent. First thing that we do is cut off the link between X and its parent and add X to the root list. You bring 5 over here and unmark it. If it was already marked, you unmark it. Then this, what is the difference between this step and this step is, when you remove this one was unmarked. That means what? It did not lose any child. First time you're going to make it marked. So there was no issue. Now this is another case where you're going to cut off somebody from its parent and it was already marked. അതായത് നേരത്തെ 26 അതിന്റെ ഒരു ചൈൽഡ് ലൂസ് ചെയ്തിരുന്നു. ഇനി നിങ്ങൾ പുതിയതായിട്ട് ഒരു ചൈൽഡ് കൂടെ കളഞ്ഞു. Got it? 26 had already lost his child earlier. That is why it is marked as black. And now you're again removing 5. Okay, you're again removing 5 as it's the second child that is going to lose. So what in such scenarios, you have to remove the parent also from its parent. Okay, and you keep on doing this until you get an unmarked node or you get a, so this is basically a recursion. You found that the parent is already marked. Why? Because it lost its child. Now you're removing a new child. So this cannot stay here. So you remove this thing and bring it to the root node. And if it is already marked, you make it unmarked also. So look at the steps. 5, I cut it out and I brought it here. 26 is already marked. So because it already lost a child before and again I cut 5. Now this cannot stay here. We have to remove it and we bring it to the root level. When you bring it to the root level, it is already marked. You have to make it unmarked. See, now it is gray in color. Now, what happened to 24? Its parent, that is also already marked and we are cutting out 26 from it. So again, it is losing a child. So this cannot stay here. So what we do, cut 24, bring it to the root level and make it unmarked. Now, is its parent marked? If this was also marked, we have to cut it and bring it and so on. We have to keep on doing this until you find the unmarked node or you reach the root node. Root node very much stop here, even if the root node was marked. Okay, so you keep, this is a recursive procedure. You can see removing this, performed a cut here. Removing this, performed a cut here. This is known as a cascading cut. In a decrease key operation, the process of cascading cut occurs. What is a cascading cut? Removal of one creates a cut in the parent, and removal of that parent again may creates a cut in the parent if the parents were also moved. So this process is known as a cascading cut. So finally, we brought all of them to the root node. Now look at the tree; it is completely unbalanced. So many nodes are there with the same degree and all. Okay, this is the final heap. So that is why this node, this algorithm is known as a cascading cut. So the cascading cut algorithm is given here. You can just go through it. It's very easy. The base thing, whether the parent is marked or unmarked, you keep depending in that. You keep on cutting and recursively call the cascading cut on its parent, and so on till you reach the root node. Okay, cut is basically removing it and adding it to the root list. That is very easy. Cascading cut is also checking its parent whether it is marked. If we have to remove this. Now checking its parent, whether it's also marked, then remove this and so on. So that involves a recursive call to cut again and a recursive call to itself also. Okay. So this is a basic algorithm of Fibonacci decrease key. Find out whether I'm asking you to decrease the key, but there is an error that the new key is actually greater than the current key. Then it is not a decrease key operation. That is a special condition check. Then you find out the key value, assign, then find out the parent of X. And if parent is not nil and you have a key, the new key is lesser than the parent, then because the parent was Y and the child is X, you decrease the value of this, then a lesser value cannot stay below, right? So what you do is you perform a cut and you call a cascading cut on Y. On Y means what? The Y is the parent. Okay. You cut this from this tree and perform a cascading cut on the parent. That is done over here. Okay. Then after this, okay, after doing all this, we find out whether the current value is lesser than the minimum of H value. If so, then the new value should become minimum of H. Why? Because when you bring all of them here, can you tell me which is the most minimum among this? Earlier minimum was 7, but once you bring all the lower values to the root level, now 5 has become the most minimum value. So you have to reassign 5 as the new min of H. So that also has to be done in step number 10. New value, whichever came to the root level, is lesser than the existing min, reassign. Got it? And this is basically the change in potential energy, you can say. This is the cost involved in that. It's basically overfund because all of them are constant. Then the last one is deleting an element. Deleting a node X is basically like the binomial delete only, Fibonacci delete. It involves the invocation of two other algorithms, that is decrease key and extract min. That is why, because extract min is called here, that is why the complexity of this one is log of n to the base 2. Okay, so what is decreasing? Why do we, when you're trying to delete something, why do we decrease it? We decrease it so that it becomes minus infinity. Minus infinity, and then you extract that minimal. That is the easiest way of deleting it. Because when you decrease suppose you want to delete a key that is somewhere below, say 52 or 21 in between. So what you do is first you reduce it to minus infinity. When you reduce it to minus infinity, naturally this node will be brought to the root level, right? So when it is brought to the root level, it is easy for us to extract the minimum node. You know, minus infinity is the most minimum among all of the root. If minus infinity also comes to the root level, min of H will be reassigned to minus infinity, and it's easy for us to remove from here. So that way you can assign. There's no need to find a separate algorithm for deletion. You can use the help of other two for doing this. And the complexity is shown here, O of log n. Okay. So this is the basic idea. I hope it is clear. Thank you.